before. We still don't understand the chemistry, so especially applying photochemical processes. And I just learned that we can now also start looking at chiral TiO2, and that will be an even bigger challenge for us in the future. I also have two home addresses, with one being St. Petersburg State University, the Laboratory of Photoactive Nanocomposite Materials, and this is where the Mega Grant laboratory is located, and the other one being the Leibniz University in Hanover, which is in the north of Germany, maybe not as nice as a city as Dublin, but also not so bad. This is my group in Hanover, because Hanover is further. I'm only showing the Hanover group. Maybe Alexei will have a picture of the group in St. Petersburg, which is quite a bit closer, as I noticed when I traveled here from Hanover. I'd like to say something about the principles of photoelectrochemical water splitting. You might know a lot of this, but maybe some of the principles are not so apparent to you. And then looking into photocatalysis, and we heard something about photocatalysis this morning already. The question is this really a single particle phenomenon, as it very often is described, or maybe it's a little bit more complicated. And then we find many systems in the literature called so-called sacrificial systems, and I have some doubts whether the research is going in the right direction here when we look at sacrificial systems. For sure we are going in the right direction if we look at multi-electron transfer processes, if we want to go for synthesis of fuels, because this is multi-electron transfer if you look at carbon dioxide reduction forming methane, for example. And if I have enough time, I will talk very briefly on photoelectrochemical water splitting with doped materials. Principles of photoelectrochemical water split. Well, this area has evolved almost 40, 50 years ago, when people first realized that if you illuminate a semiconductor and you have this semiconductor connected to a counter electrode, then what you can see, and you illuminate it with light exceeding the band gap energy, you can promote electrons from the valence band down here to the conduction band. These electrons travel to the counter electrode, where they then will be able to, for example, reduce protons to form molecular hydrogen, while on the surface of the illuminated semiconductor you can oxidize water forming oxygen, so you can split water, for example, forming molecular hydrogen and oxygen. And if you do this nicely and quantitatively, you can store the incoming energy, for example solar energy, into a fuel which is hydrogen, and you can then burn this afterwards or use it in a fuel cell, whatever you like to do with this fuel. You can also couple an N-type and a P-type semiconductor, illuminate both of them in a so-called tandem photoelectrochemical setup. Once again, you have connected both of these materials, and if you do this right, then on the N-type material you form your oxygen, and on the P-type material you form your molecular hydrogen. Here you require two photons, both of which have a lower energy than the system I showed you before, where you need to have at least the energy exceeding the 1.23 volts which you require for breaking the bonds. What are the ideal semiconductors that we need. Well, the ideal semiconductor for the first system should have the upper level of the valence band here, the lower level of the conduction band up here, with these two levels being the reduction and the oxidation potential of water respectively. What you see here are the over potentials for oxygen formation and here the over potential for hydrogen formation. If you use a tandem setup, then you can combine two semiconductors. They just need a little bit of overlap here. Here you have the oxidation of water and here you have the reduction of water. So these are the ideal systems. So we know from theory where we need to go. It's yet up to us meaning everybody in this world, to find the right materials, and we are still far from being there, even though this research, as I said, has been started some 40 years ago or so. Now we take the transition from electrodes to particles. Well, in principle, you can do the same thing. Take a semiconductor particle, illuminate this. Now you don't need any wires anymore. All you need is the right position of the valence band and of the conduction band to then reduce an acceptor, for example protons, and oxidize a donor, for example OH minus, and at the same time you will be able to split water on a single particle, provided you are able to prevent electron-hole recombination in the system. You see the system, if you look in the real world, you see there are lots of problems around. First of all, photons need to be absorbed well. You need to construct, and I think the talks we heard before showed this quite clearly, you need to construct the surface right, because all reactions happen at the surface. That is extremely important. You need to prevent charge recombination, so you have to ensure that the charges that you produce in the bulk of the nanostructures actually make it to the surface, where you would have additional catalysts. Very often in photocatalysis they are called co-catalysts, but I have been in the community of catalytic people, and they told me there is no such thing as a co-catalyst. They are catalysts for electron transfer for reductive and oxidative processes respectively. All these materials and many more have been tested as potential photocatalysts, and there are some materials which really nicely, as a nanoparticulate system, split water. But as you see here, most of these materials have very wide band gaps, so they are nice for the laboratory where you have UV lamps, but the amount of UV light, even if we depleted our ozone layer completely on the Earth, we still don't have enough UV light of, let's say, 4.7 electron volts available, so we definitely need other materials for visible light applications. But for example, tantalates have been shown to be really strongly active systems for water splitting, but still this happens mainly under UV illumination. Well, you can also take your particulate system and mimic a tandem cell in the so-called photocatalytic Z-seams system, where you have one particle where only the reduction takes place, another one where only the oxidation takes place, and have a sensible redox system. Most simple one being, for example, iron 2 and iron 3 to do what the wire is usually doing in the electrode system. Visible light applications, people have been able to shift the absorbance into the visible, but in most cases, and I will talk a little bit more about this in a minute or two, people have just taken so-called sacrificial systems. So they have just looked at the reduction of water, and they didn't oxidize water, but they oxidized, for example, sulfide to sulfate or sulfite to sulfate. And when they were looking at the oxygen formation, they once again used sacrificial systems, and this is the most popular one, reducing silver to silver metal. These are some examples, again, taken from the literature of visible light photocatalysts from very well-known laboratory of Professor Doman in Japan, and he showed that his systems were actually able to split water. However, even though this system, this nitride system, absorbed nicely visible light, as shown here, actually only the UV part was able to split the water, and the visible light one was a zero line here. No water splitting occurred there. He was able to change that, changing from nitrides to oxonitrides, and these are actually the first systems which can use visible light in a nanoparticulate system and really splitting water into hydrogen and oxygen, and this depends, these are systems here now with different catalysts, not co-catalysts, different catalysts on the surface, and some catalysts work well while others don't work well at all. One catalyst that has been developed to replace something very expensive such as platinum is nickel oxide. Nickel oxide seems to be a very good catalyst for hydrogen formation. And the most likely mechanism, the mechanism is still not completely sure, but the most likely mechanism is that the nickel 2+, which you have here in the system, is reduced as a single site into nickel 0, and then the nickel 0 actually reacts with 2 protons forming molecular hydrogen. So catalysis also is something we need to learn a lot about. So is photocatalysis really the single particulate phenomenon that I've shown you here? Well, we don't think so. We have a lot of evidence that there is a self-assembly of these nano structures, but not in a very random way, but the nanostructures self-assemble. They seem to know the crystal structure of their neighbor, and so they self-assemble into nano wires, little single crystal nano wires, and what we are pretty sure of is that you should not neglect something like an antenna phenomenon, very well known in many parts of other chemical systems, photochemical systems, where one particle might absorb the light. You can have an exciton transfer through a three-dimensional network of these self-assembled nanoparticulates until finally you find a structure where you have the right conditions for the surface reactions to occur, here shown as a surface reaction for the oxidation of methanol and the reduction of oxygen. Not only can you transfer excitons, which is electron hole pairs, through these self-assembled nanostructures, but we have also shown nicely that you can transfer electrons through these nanostructures. This is very similar to what happens in dye-sensitized solar cells. Sacrificial reagents, why am I so skeptical about them? What we want to do is really to split water, but what you find in the literature is that you just look at oxygen formation or at hydrogen formation and work in the presence of sacrificial reagents. Is that a good idea? Well, here are some sacrificial reagents for oxygen productions. As I mentioned earlier, silver ions are used, and besides sulfite and sulfite, alcohols are very frequently used when you want to look at hydrogen formation. What is the problem? Well, the problem is that the chemistry, even though these are very simple molecules, the chemistry is not that simple because you might just oxidize the alcohol with one hole, forming this alpha hydroxy methyl radical, and these radicals they love to get rid of another electron, they are so strong reductants that they can easily inject an electron into the conduction band up here, making them into what is called current doubling reagents. And so you use one photon, and this one photon generates two electrons up there. First electron from the electron hole pair, second electron from this alcohol radical. And so one photon is able to produce a hydrogen molecule, and this should not be the case in case you don't have an alcohol present. Okay, we looked at these sacrificial systems and looked at them for a long time, and as you run out of alcohol, you run out of reaction. So the reaction only goes in the presence of the sacrificial. Here once again I show the mechanism, and how about all these sulfide systems? Well, the same thing happens as you oxidize a sulfide or a sulfide with one electron, you form strongly reducing radicals, even more strongly reducing than the radicals that you form with the alcohols, and again you can have the current doubling effect happening. Here is one system that might be more suitable. If you have no proton here in the alpha position of the alcohol, then you cannot have a current doubling. So if you use such a tertiary alcohol, that will be much more suitable to understand really the chemistry going on. What's wrong with a silver system? Well, silver cannot only be reduced to form silver 0, but it can also be oxidized to form silver 2+. And this is old chemistry. It has been shown that silver 2+, look in the old textbook of inorganic chemistry, forms silver peroxide. So silver in its own right might be a catalyst, a molecular catalyst for the oxidation of water. So you try to just study what happens there, and you put a catalyst, so you change the system. Once again, maybe not so clever. The same thing you can postulate actually with iron 3, not only being an electron acceptor, but it's also an electron donor, and iron 4 or even iron 5, I talked to our inorganic chemists, can be involved in this reaction. This is a crazy compound, peroxide disulfate, very often used in these systems. Look in the literature, peroxide disulfate, when this is reduced, forms a sulfate radical. And the sulfate radical, according to my knowledge, is the only beast that is a stronger oxidant in water than the hydroxyl radical itself. Because as it is formed, it reacts with water, the surrounding water, forming hydroxyl radicals. So once again, current doubling is sort of inherently built into the system. So better use electron acceptors like carbon tetrachloride or maybe tetranitromethane or something like that. So this just summarizes my skeptic way here. Multi-electron transfer. How am I doing with time? Do I still? Another 5 minutes, great. Multi-electron transfer, that's what we need. 2 electron transfer to form hydrogen, 4 electron transfer to form oxygen, 8 electron transfer to reduce CO2. Can we mimic such systems? Here I now go to TiO2, what was introduced by the previous speaker, a nano TiO2, very easy reaction. If you just react titanium tetrachloride with water, you form anatase at ambient temperature, and you can make these particles blue. And what does blue mean? You load them up with electrons, and it's extremely simple. It's something you can do with, I think, first first grade students in the laboratory. You prepare this TiO2 and you illuminate it in the absence of oxygen and in the presence of the alcohol. The alcohol is oxidized, I showed you this before, and the electrons have nothing to react with because you don't put a catalyst, so you don't form hydrogen. You don't have oxygen, so you cannot reduce oxygen, so the electrons form this blue color, which is just the trapped electrons on the titanium sides in the form of titanium 3+ ions. This goes linearly with illumination. This is the strong blue color that you're forming here, extremely broad absorption spectrum. You can determine the rate, and you can determine the extinction coefficient, so you know exactly how many electrons you have per particle. And per nanoparticle you can have 20, 30, 40 electrons easily on a single particle, and then you have this three-dimensional network. So multi-electron transfer processes should be easy to follow. So we looked at the kinetics here, and these are the kinetics. The reaction with oxygen, you see as you put more oxygen, the color depletes more quickly of these electrons in the TiO2. Nothing happens with argon, and not only does it deplete more quickly, but more of the color depletes because you have more oxygen present, and it depletes until all the oxygen is gone, and then you have still the excess electrons left. All these experiments were done with excess electrons, so you can do this with oxygen, with hydrogen peroxide. You can also do it with nitrate, and you find that you transfer, I put here 7.9 because that's our measured number, but that would be 8. So you transfer 8 electrons to nitrate, going all the way to ammonia in the systems, 2 electrons to copper 2+ to go to copper metal. If you, for example, put silver metal into the system, you find a very slow build-up of the silver metal islands on the surface, and then the reaction speeds up, and what you see then at the end of the reaction is the formation of molecular hydrogen in the system. And finally, just a little glimpse of the doping effects in photoelectrochemical water splitting. What we have done here is use aluminium doping of TiO2, and it's interesting to see here that at about 0.5 weight% of aluminium you get the highest efficiency, and this is probably correlated to the position of the flat band in these aluminium doped TiO2 systems. Fluorine can also use as an anion for doping of TiO2, and if you once again look here in the water splitting system, you find that you get a higher efficiency of water splitting with the fluorine doped systems. That brings me to the summary of my presentation. I hope I could introduce the principles of photoelectrochemical and photocatalytic water splitting to you. I'm pretty convinced that the answer to this question is no. Photocatalysis is not a single particulate phenomenon, but works with quite complex structures, self-formed structures of particles. If possible, people should avoid sacrificial reagents. Multi-electron transfer, I think, is an important process, and it's it can be quite easily shown with titanium dioxide. And finally, I introduced some doping effects of titanium dioxide. So I like to thank all those of you who are here, and I like to thank those people here in Russia from the Mega Grant giving us the money, and those people in Germany providing the money, mainly from the German Ministry of Science and Technology. Thank you very much.
Very interesting work. It is clear one of the most important topics for the future, because we need to produce the energy from the sun to do this job.
Thank you very much. I hope the Mega Grant Commission sees it in the same way. Thank you.
And it is clear that we are dealing with very, very complex composite material. And I wonder if, in order to get really fundamental understanding of what is going on in so complex systems, I would like to have your advice. Which are the characterization techniques that will be important to study under, let's say, working conditions of the system? I guess you need space resolution. Probably you need also time resolution to see what happens between dark and light and so on.
Exactly. You're absolutely right. And today I had no time to talk about these works that we are also doing. We are working with time-resolved laser flash photolysis spectroscopy. And once again there, when you go more deeply into the system, you find out that they can be really complex, because some of the photon energy that you want to use for your analyzing might actually even change the structure of your material. Very often we are working with a structure of the material which is not the thermodynamically stable one. For example, TiO2, which was mentioned by me and previous speaker, the most active structure is the anatase structure. The thermodynamically stable one is rutile. And in a photolytic process, parts of the anatase that you want to study might be converted into rutile, then again complicating the system.
Thank you.
Okay, let's think.